All right, welcome. In this video, we're going to take a look at two problems that are very closely related, so it's really only one solution we're going to look at. The subset sum and the partition problem, and we're just going to continue looking at, again, two-dimensional dynamic programming. So we're using these two problems as a backdrop to continue talking about dynamic programming. So to start out, let's just revisit again the dynamic programming design strategy. And once again, let's just remind ourselves that the first three steps here, finding the self-reduction, the reduction from the main problem to the subproblems, has been the key step for both divide and conquer and dynamic programming. But again, in dynamic programming, if we just choose we want to do a bottom-up, or maybe we get to step 4 and we identify overlapping subproblems in a top-down recursive solution, that usually indicates to us that we should do bottom-up dynamic programming. And what that means is we're going to use a data structure to store the solutions to our subproblems, and we're going to iterate through those subproblems, usually starting at the simple ones up to the hard one, the complex one that we're trying to solve. In the end, we'll perform a little bit of analysis, and usually, again, the analysis for dynamic programming algorithms is usually fairly straightforward, since they are usually just a couple loops, a loop or two, nested loops, something like that. All right, so let's take a look at our first problem here. Let's say you have a set of positive integers, and you also have a target. And you want to know if there's any subset of that set of positive integers that adds up to your target value. So in this example, we have 5 different numbers, 5, 7, 2, 3, and 9 in our set of positive integers. And we want to know if any of them add up to 13. So this is really an instance of our problem, or an example input, so that's going to help us express the problem formally. But we're gonna, maybe we should just try and explore the problem a little bit here. Let's see if we can find a subset of this particular set that adds up to 13. So take a minute if you'd like. And if you have taken a moment, you may have frustrated yourself a little bit. As it turns out, there's actually no subset that adds up to 13. However, if we wanted to prove that to ourselves, we'll maybe notice something here. There's an asymmetry. If there were a subset that added up to 13, it's as simple as finding it. If we could find it, I could show it to you, you would believe me. However, if I claim here that there is no such subset that adds up to 13, the only proof that you should accept, not my word for it, would be a list of all possibilities and showing that none of those possibilities add up to 13. So this would be what we would call exhaustive. We want to exhaust all possibilities and show that none of them add up to 13. If that were the case, then you would hopefully believe me that there's no subset that adds up to 13. And since I claim there's no subset that adds up to 13, in the absence of trying all the subsets, the only other option we have is maybe having an algorithm of some kind that might help us do that. Alright, so if we want to formalize a subset sum, what we'll see is we've already got an example instance over here that gives us a good way to set it up. So first of all, we're going to have a set S, and I'm going to call my set S. And I'm actually going to talk a little bit more about it, give some notation. I'm going to say S1, S2, up to Sn. By writing it in that way, it gives me a nice convenient way to refer to them. I can now talk about SIs and so on. So this is a good setup. And maybe I should say what it is. I'm going to say is a set of, and let's be careful here, positive. We said it was positive in our write up over here, of positive integers. Okay. That's not it actually. So let's add a little bit more here, and because we see here that the set of positive integers is an int, we also have this target. So I'm going to say T a target sum. And that sort of matches our write-up up there. So if we want to now consider what our output's going to be here, well, this output is actually kind of, we haven't really said what it is here. It says you have a set of positive integers, a target sum, and you want to know if there is a subset that adds up to the target. That doesn't say that we actually want the set. It's just asking us sort of a yes/no. So one possibility here, so we could just sort of have a yes/no situation. Yes in this situation, no in this situation. And this type of problem, that's sort of a yes/no problem, we have a special name for them. We call them decision problems. And in foreshadowing a little bit in a future video, we're going to talk more about decision problems, and we might come back and look at subset sum as a decision problem, as we have it here. But the way I actually want to focus on it now is not quite as a decision problem. It's still going to have a decision problem like structure, but I want to remember that, as we're studying dynamic programming here, and a lot of the dynamic programming algorithms that we've looked at so far have been optimization problems, and they've sort of had two components. They've had the optimization part, the min or the max, and then they've had how do you achieve that? What days do you work, or how do you put the lists in a particular order? There's different ways to achieve the min or the max that we've been trying to calculate. So here we don't actually have a min-max, we have the true-false, the yes-no. But in the yes case, if there is a subset that adds up to t, we probably want to know what it is. And there's actually going to be a couple ways we could set this up here. I might say an S prime subset of S. Okay. In fact, why don't I do that? S prime subset of S. And we'll just take a look at a couple different ways we could set this up. So S prime is a subset of S such that, so not any old subset will do. We want a subset such that, well, we want to say if we added them all up, they add up to the target. That's the goal. So luckily we have a summation tool that'll let us do that. So sum, and now again, we're used to maybe doing an I equals 1 to n kind of thing here. But because we're talking about sets, we can use the set. So I'm going to say S as an element of S prime. All of the S's that are in S prime, let's add them up. It should equal our target here. Okay. So we want S prime such that this is true, but that might not exist. So we should say maybe here at the I'll finish off this little bit here. Should be if S prime exists, but if it doesn't, here's where I'm going to say no, or false, or even error, depends on how you've got this set up. One of these will respond otherwise. Okay. So again, we have a choice of how we want to respond in the case where this subset doesn't exist. We probably have to respond some way, but basically saying there is no such subset. But if the subset does exist, how do we want to characterize it? This is one way. There is another way that we could characterize this, and I'm just going to maybe write this second version down here before we move on. Is I've been using these index sets up till now. Now I've got this set up as a setup here as a set. This makes sense to use subset notation, but if I had set up my input as we have in other problems as though it was a list, not written with set notation, we might want to use an index set instead. So another way we could do it is we could say my output should be this index set A telling me which elements it is, but then it makes this writing this little bit different. So let's try writing this one. So again, such that, maybe I'll just write it here. Now we're going to do for all the I in A, I'm picking this notation on purpose. These are supposed to be indexes, so I'm using the letter I to say they're indices. Now here, where I was just summing over all the S's in this subset, Here, these indices are picking out elements in this subset, so I need to be careful. It's S sub I should be equal to T. Okay, so again, we want that index set such that if we added up the elements relative to those indices, we would get the target. So these two things mean the same thing. Okay, so if you formalized yours in a slightly different way, it doesn't really matter. What matters with the formalization is that it gives us a nice, convenient, precise, concise way to express ourselves when we want to talk about it. Okay, remember our next step is to try and find some kind of reduction from the main problem to the subproblems, and so we want to have a clear way to express our output in that case. In this case, we don't have a min-max, we have a yes-no. Okay, and in the yes case, we want to recover the solution. What we're talking about here is the solution we want to recover, but in the no case, there's nothing to recover, so we don't need to worry about that. In the yes case, we want to figure out how we want to describe that output. All right, so we see my expression here on the slides is a little different, but it uses that index set that we were looking at there, and it shows a slightly different way to formalize the problem. So of course, as I mentioned, either of those, any formulation that is at least precise and correct is acceptable. All right, so the next bit is, let's see if we can explore some possible solutions to this problem. So this problem is actually sort of historically well known to be a hard problem for at least the last 50 years, has been sort of at least enshrined as a hard problem for that long. So let's see if we can try and solve it. So the first question I have here is, let's see if we can do a brute force algorithm. And let's remind ourselves what that means. Brute force really means exhaustive, means try every possibility. So if we want to try every possibility here, that means we need to try every possible subset of S, or every possible subset of the index set that we have here. Both are the same size and both correspond to each other. It's the same problem. So one question then that arises is, how many subsets then are there for a set of a given size? Well, if you can remember your set theory, you're going to remember that when we're talking about the set of all subsets, this has a special name. We call that the power set of S. The power set of S, we write it in this way. Okay, so if our S is up above here, has n elements in it, our power set of S is going to be the set of all subsets. But what we're asking is, how many of them are there? How many of them? Well, if there are n such subsets, n such elements in our set S, then how many subsets are there is actually 2 to the n. And we can see this in one way. The way that I like to remember it is, if we have these n elements here, if we want to pick out a subset, for each one we either get to pick if it's in that subset or not. For instance, we could pick for all of them to be in, that would give us this set here. Or we could pick for all of them to be not in, that would give us the empty set. Or any other combinations in between. Now each one of those, there's a couple ways for us to think of that, but we could sort of think of that as a yes or a no for each one. That's 2 options, and we have 2 times 2 times 2, 2 to the n. That's what we get up here, and the n is equal to 2 to the n. Another way to think of it is, every time a number is in there, it gets a 1, and every time it doesn't, it gets a 0. Then what we're creating here is an n-bit number, and we might think, well, how many n-bit numbers are there? Oh, there's 2 to the n. So there's more than one way for us to remember this, but it's a very convenient thing to remember. The size of the power set, or the number of subsets of a particular set, is exponential. That's the key bit here. And the reason we want to take this away is, anytime you're facing a problem where you're saying, well, I need to find a subset that does something, anything, in this case it's add up to a target, okay, but maybe you need to find a subset that is less than something or greater than something. Those are a little bit easier problems, but if you go ahead and try and say, well, I'm just going to try every subset, well, you put yourself at risk of running an exponential number of checks, and we don't really want to do that. And that's sort of the purpose of this exploration, is to say, is this worthwhile for us to explore the brute force solution? So we came up with 2 to the n here. How many additions does it take to check each sum? Well, this is the second piece that we need to take into mind. Even once we found that subset that we want to know if it adds up to t, we still have to add all those elements together. And the way we do that is by just computing a sum. And of course, computing the sum is going to take time. And in this case, it's saying, well, we're just talking about integer additions, but it might be even worse than that. But this is going to be about order n times. So putting them together, we actually get about order of n times 2 to the n for our brute force algorithm. Now this seems pretty bad. Usually when we get an exponential runtime, at least my advice would be, well, that's a bad algorithm, throw it out. Turns out for this particular problem, the subset sum problem, it's a special category of problem. It's a problem that's called an NP-complete problem. And I'm going to have a few videos coming up talking about NP completeness. So stay tuned for those if you want to know more about that. But NP complete problems for now, the sort of catchphrase that I like to attach to them, it's a little technical, at least you can screw it up and get it wrong, but the catchphrase that I like is our best known algorithms. That's the first bit. Our best known algorithms are exponential in their runtime. So our best known algorithms are exponential in the runtime. So any problem that's NP complete, our best known algorithms are exponential in their runtime, or worse, meaning that we find since they're our best known algorithms, that's the first bit that's key, it means we haven't found any better algorithm, any algorithm that is faster. That doesn't mean we're not going to find another algorithm that's faster. Someone who's bright might be able to find one. There are those of us, myself included, who after spending enough time studying computer science and these problems have come to the internal conclusion, I believe, that for instance this problem subset sum, we will never find a better algorithm than an exponential time running algorithm. But my belief doesn't make it so, nor does the belief of even 100 computer scientists. We are all waiting for a proof that this is so, and we do not have one yet. So that might be you. You might be able to provide us a proof that that is so, or you might be able to shock and surprise us all by, we all think that you're not going to be able to come up with a algorithm that's, say, polynomial in time, but maybe you can. Go ahead and find one, and if you do, guess what? There's some money at the end of the rainbow for you. You can collect that and probably collect a PhD if you want one of those as well. But if you have a solution and you think it's right, my advice is always send it to me first, and I'll double check it. And if it's right, I'll let you know. Okay? All right. Well, this brute force algorithm obviously is not going to be up to speed, but we're going to come up with a slightly better algorithm. Our algorithm, unfortunately, in the end, we should not expect it to be polynomial, because, as I've just sort of argued here, our best known algorithms are exponential. So we should be suspicious if we think it's going to be polynomial. So follow along, see if you can come up with an expression of the runtime as we go, and at the end, when we're done here, I'll try and argue a little bit about what we do know about the runtime. All right, so one of the first problems we're going to have to look at if we're thinking about doing dynamic programming or divide and conquer is what subproblems should we look at? And so for our problem here, or the way we formalized it elsewise, they're equivalent. What subproblems should we look at? And actually, in problems like this in the past, the ones that we've encountered so far, we've chosen to do one of maybe two possible things here. We could limit the list. In this case, we're saying n becomes maybe n minus 1, or in some cases n over 2. But our n becomes n minus 1, meaning we shrink our list, make it one shorter, and we consider solving that simpler, hopefully, problem with less elements. Another dimension that we might be able to restrict our input here is this target integer. Now, in the past, restricting the target integer maybe doesn't make sense. So for instance, a similar problem to this, at least in its input, is the search problem. In the search problem, we are given a list and we're given a target, and we're supposed to search the list for the target. Now, in that problem, there's a number of actually recursive ways we could solve that problem. We looked at, I think, one or two of them, actually three of them in an earlier set of videos. For those recursive solutions, it made sense to restrict the size of our list. Maybe to an n minus 1, maybe to an n minus 2. We didn't think of that one, but we could probably come up with that too. Or n over 2, that's one that we looked at as well. But we never changed the target. For that problem, it doesn't make sense to change the target. Searching the list for something other than what we're looking for isn't going to help us. Maybe in a binary search scenario when our list is sorted, but even then, we would rather just search for the actual target than searching for something nearby, say. However, in this problem, we're going to find that restricting both of these dimensions makes sense. Restricting the number of elements in our set, that obviously makes sense. Finding subsets of smaller sets is easier than finding subsets of larger sets. But we're going to also find that finding subsets that add up to something smaller than our target might be useful. Adding up to larger than our target, probably not. But finding subsets that add up to something smaller might be useful because, and here's the key insight, we can add an element to that subset that adds up to something less, and it will get bigger. It will get bigger, and it might, say, become t. So it might be useful to look at smaller subsets that add up so we can place an element in there that would add up to t. So actually, when we're thinking about this, we're going to reduce this set to a smaller set, and we're going to restrict our target in both dimensions. So this is what's going to make our solution here a two-dimensional dynamic programming in the same way that our previous couple examples have been two-dimensional. We're going to restrict both. So as a result, I'm going to use this SS subset sum of n and t. These are my two inputs. Well, remember, my input's actually the full set, but to save ourselves some keystrokes and some writing, we don't need to include that here. The only part that we're going to restrict is n to n minus 1 and so on. And we might also restrict t as well, t minus something. Okay, so those are the two dimensions we're going to use, and I'm going to use this to express the output. But here I'm also going to say we're only going to decide if the subset exists. We're only focusing on the yes-no part. If it exists, we'll go back afterwards and find our A, or find the subset. Okay, so now the effort we have must be go into coming up with a self-reduction. So let's try that. All right, let's consider the self-reduction that we want to build here. And remember, we can really start it on either end. Start on the recursive side or start on the terminating cases. I usually start with the terminating case. It just helps me start thinking about the problem a little bit. And so in this case, again, I have to make choices of what my terminating case is going to be, what values of n, for instance, and t I might want to choose. And I might want to start simple. We're going to want to decide how we want to start. Do we want to start down on the sort of lower end, the simple end? or up on the high end, the recursive end. So actually here we can sort of think, I'm going to think of my set here coming in as a list. Here we got our S1, here we got our Sn, and we want to think, okay, I'm going to actually start on the easy end. We could consider if we had S1 here by itself, and then treat that as our terminating case or base case. That would be an n equals 1 kind of scenario. Or we can treat the n equals 0 scenario, which is when we have no elements at all, the case where we've been given an empty set. In which case, and maybe this is worth thinking, if we have an empty set, what do the subsets of the empty set sum up to? Well, they sum up to 0 by default. The empty sum is 0 by definition. And so that maybe leads me to the first condition that I want to consider. If my target is 0, then that means I'm gonna answer true and false. I'm gonna answer true if my target is 0, because if my target is 0, the empty set is a subset of every set, and the empty sum is always 0. So this is always something we can achieve. Okay, but what if t then is greater than 0 and n is 0? So n is 0 was the case we were considering here, where we had no elements at all. We were given an empty set. The only target we can reach if we're given the empty set is 0. So otherwise, we should say false. All right. So what does this leave us with? We've got t greater than 0 here, n is equal to 0. So if that's not the case, we must have if t is greater than 0 and n is greater than 0. And that's starting to look like our recursive case. So we need to get to in our recursive case. All right, so in our recursive case now, we started thinking about this while we were sort of problem solving a little bit earlier. Once again, in coming up with our self-reduction, what I want to do is I want to think about the possibilities, but only focus in on S of n here. Okay, what are we going to do with S of n? Well, S of n, let's think about our solution case here. Let's say there is a target, there is a subset that adds up to our target. If there is, S of n is either in that subset or not. It's either in or it's not. Now, often, at least I've found with some of the problems that I've explored, the not case sometimes is a little bit easier. Okay, so let's think about the not case. So if S of n is not in the S prime, then what we know is S prime must be a subset of S1 up to Sn minus 1. Because we know Sn, by assumption here, we've just assumed we're in the case that it's not there. So that means S prime must not be a subset of all of them. It must be a subset of the first n minus 1. Well, actually, we can write this down. That's saying if there was a subset of the first n minus 1 elements that adds up to t, then there must be a subset of all n elements that adds up to t. That makes sense, right? So if there was a subset of the first n minus 1 elements that added up to t, of course there must still be one when we add Sn into the list as well. We don't need to use Sn. Okay, but remember that was only one possibility. The other possibility is that we did use Sn. So if we did use Sn, then we know that Sn is inside of S prime. All right, in this case, let's write it slightly different. Let's say our S prime in this case, we know that it's going to be, it's going to contain S sub n. But then we're going to union onto it some other subset, S double prime. Well, all the elements of S double prime must come from the remaining elements, right? S1 up to Sn minus 1, just as we had before. So this subset must be, just like we had for above, must come from, and here maybe I'll write it here, SS, from the first n minus 1 elements as well. Okay, this subset. But this subset does not add up to T. It does not add up to T because S prime adds up to T. This one adds up to T. This one adds up to T minus whatever this value is. Well, we know what value that is. We just call it Sn. So our other problem, sub-problem that we've encountered here, if we do include Sn, is we'll look back to see if there is a subset that adds up to T minus Sn of the first n minus 1 elements, then what could we do with that subset? We could add Sn in. So that other subset was this, what we were calling S double prime. We'll add Sn in, union these two sets together to give us S prime, and then S prime should add up to T, right? This plus Sn, cancel, cancel, gives us T. Okay. So one of these, so basically what we're saying is, in our main case here, we can make a subset of the first n elements that adds up to T if one of two possible cases occurred. If we could already make a subset of the first n minus 1 elements that adds up to T, or, I need to write the or in here because this is how we're going to join these two together, or if out of the first n minus 1 elements there was a subset that added up to T minus S of n. And if there was, we'll call that one S prime, we'll add Sn in, and that will give us a subset that adds up to T. So these are the two cases that would lead to us having a subset that adds up to T. And they're the only two cases that would lead us, because here there's only two possibilities for our Sn, and we considered both of them. Okay. So these two subproblems are the subproblems we'll look at. We'll notice both of them restrict n minus 1 and n minus 1, but this one restricts S of n as well. No, sorry, it restricts T as well by subtracting off S of n. How do we put them together? Well, this is sort of different than some of the problems we've been looking at so far. This is a logical problem. It's giving us Boolean output. So we need some kind of logical operator to put them together. In the previous ones, we've been minning or maxing. Well, it makes sense that we're going to and or something like that here, and it turns out it's or that we want. If either of these cases happen, then we have a subset that we're looking for. All right, let's see if we can write some code then. And again, we're just doing this to practice our taking our self-reduction and turning it into dynamic programming code instead of recursive code. This recursive structure here suggests recursion, but we are actually going to have some overlapping subproblems in here, and it might not be immediately clear, but maybe I'll point that out as we go through our solution. So we don't want to do recursion in this case. We want to indeed use our dynamic programming. So let's get ourselves something to store our solutions to our subproblems in. I've already used S here, so I'm actually just going to call it A for simplicity here. And my list A here, since I started here at 0 and 0 in both my cases, I should be careful here. I'm going to go 0 up to n in my first dimension. I'm going to go 0 up to t in my next dimension. Okay. All right, after our declaration, we've got a data structure to store the solutions to our subproblems. So now we just need to initialize it. So the first loop I'm going to do, I'm going to vary my first variable from 0 to n, and I'm going to use I as my index to iterate over that. So this would be the case where I'm going to set my t to 0. So I'll just say let a, in this case sub I, since we're setting in our first variable, we're subbing in with our index I, but we're setting our t to be 0. So I'll be just setting these to be true then, in this case. So the next loop that I'm going to do is going to handle the case where our n is going to be equal to 0, but our j is not. So I got this wrong. Let me fix that. So we'll start with our j of 1. We'll let this first loop handle the 0, 0 case, which we want to set to true. But all of the other ones when t is greater than 0. So let's go ahead and do those ones. In this case, we were saying it's when n is 0. And we'll use j to sub in for our second index. And we'll set all these ones to false. So this is our initialization. So now all we have to do is do our iteration. So I've set up two nested loops here. My first one, iterating I standing in for n from 1 to n, okay, and j standing in for t, again from 1 to t, okay. And we'll use, well, I kind of messed it up there, but let's write it and get it started here. We're going to be setting our values for a of ij, and it's going to be equal to something. Let's go back and check. It's going to be equal to, we're going to take these two subproblems. These look recursive here, but these are going to be our lookups. Okay. Remember our I in for n, our j in for t. So we have two lookups we need to do. Our first one was I minus 1 j, and then the next one we're going to do an OR. Since this is code, I'll use a logical symbol here. Or a I minus 1, still going back to I minus 1 in that second case, but remember the next one was going to be j, so it was t minus sn, but here instead of t we're going to have j, and instead of sn we get si, because we're currently using the index I to sub in for n. Okay, this is going to overwrite. This is a logical OR, so we're going to look up to see if there's trues or falses here. If we get any trues, we write trues, otherwise we write false. So then what do we want to return? Well, our answer is just stored in the last location. It's either going to be a true or a false. And so we're going to return here a sub n sub t. Okay, now if we're looking at this code, it's not too different than code we've looked at before. And so maybe we're saying, okay, haven't we done something special here? Let's do a quick analysis. This is n, this is t, this is n times t. That doesn't look exponential to me. Am I wrong? Did we solve the problem? Did we win the $1 million? No, we didn't win the $1 million. The reason is that t here is smuggling things in. Remember, I've actually written t as a capital to try and tell us how big it is. Okay. Now, the reason here is t is an integer. So for instance, in my example, my t was 13, which means that if we had to build this matrix, and we will in a second, it's going to have 13 rows or columns, depending how you orient it. Actually 14, since we started at 0. Okay, that's quite a bit, since we only had 5 elements in our subset, or in our set. The other thing we'll notice, though, is to write down 13, at least the way I've written it here, is it's 2 digits, too big. Or, if I wanted to write it down in binary, it's 4 bits. And we might remember that the number of bits it takes to write down our number here, t, so let's go ahead and make a lowercase t now. Lowercase t is going to be the number of bits it takes to write down t. Well, that's going to be log base 2 of t plus 1. If you want to know digits, go ahead and take log base 10.
that's an easy one to calculate. Log base 10, the floor above this, well, you get 10, and that's 1. Add 1 is 2, 2 digits, that's how many digits it is. Bits, well, if you got your log base 2's down, then you can probably calculate your bits pretty easily too, okay? But in any case, when we express our runtime then, we should express it in terms of the actual size, which is lowercase t here. And, you know, with waving my hand at some plus and minus ones or some constants here, we could roughly say that t is 2, not 2 to the I, 2 to the t. So this here is theta of n 2 to the t. So there really is an exponential part of this runtime here that is sort of hidden. Okay, especially if we don't write that as an uppercase t and write it as a lowercase t, we start to forget that the number doesn't represent its own size. The number of bits in the number represents its size. Okay, so that's why our solution here doesn't win us $1 million or solve any outstanding problems, but it is a good application of dynamic programming. So what I want to do is finish with a quick example. So I think this is similar code to what we just came up with. But now what I'm going to do is I want to solve an example. So here I've got the example we started with. My target's going to be 13. I'm going to hopefully prove that there is no subset that adds up to 13 by running our algorithm. Okay, so we're also going to use our S here, and for the sake of just saving myself a little space here, I've drawn my N going down and my T going off to the right, and we've got 0 for my N here, meaning 0 for my, this is 0 for my T here. This was our first initial case where we set everything to true, all trues in this column. And then this row here, after the first true, for N equals 0, all false. That's our second initialization. So we do both our initializations here, and we're ready to go. Okay, so everything else we're doing is inside the main loop, and inside the main loop, we're doing this OR, logical OR. Okay, now this algorithm, like the next one we're going to look at too, is going to have an offset. At each point, we're going to be looking at two subproblems, and let's be careful here. The first subproblem is in the same J, which is the same column, but the row above, I minus 1. The other subproblem is also the row above, I minus 1, but it's offset. This is what I'm talking about. It's in the same column, but offset to the left. By how much? By whatever S sub I is. And so I've written S sub I here that's telling us what our offset is. Okay, so in the first one, we have two subproblems. One immediately above, and one offset by 5. Okay, so some of us might notice, hey, that first subproblem, the first time we do that, we get out of bounds then. What are we doing with that? Well, once again, one of the joys of dealing with algorithms instead of implementation is in the algorithm, we don't need to worry about out of bounds. I mean, we should worry about it a little bit, but we don't have to put a whole bunch of error checking about out of bounds as long as we have a reasonable assumption about what happens if we go out of bounds. So let's see if we can come up with a reasonable assumption. First of all, what are we doing with these subproblems? We're sticking them in an OR. So usually what our reasonable assumption relies on is what are we sticking them into? A min, a max, an OR, an AND. Depending on what we're putting those subproblems into, there's usually some safe additional input. So in this case, in an OR, if we put a true into an OR, it messes everything up. Everything becomes true if we put a true in. But if we put a false into an OR, it depends on everything else in the OR. If everything else in the OR is a false, then it's false. If everything else in the OR is a true, then it's a true. So putting a false into an OR is safe. So what we're going to assume here is that outside of our matrix, out of bounds, is just filled in with all falses. Okay. So that makes our first subproblem kind of easy for us to do. We're going to look above 1, and we're going to look at an offset. 1 minus 5 is minus 4. That's out here. What is it? It's a false, because we've assumed everything out here is a false. So false and false is false. And so what we'll see now is that as we're solving our subproblems, we kind of have one counter that's lockstep with us, and then the other one's just offset behind us by 5. Okay, and it's just sort of following behind. And so we can, if we go along as we're running along, we're just comparing those two values and doing the logical OR. So again, false and minus 3 is false, so false. False and false is false, and we notice those falses keep coming until we get here. The two subproblems are false, and 5 minus 5 is 0, and we get a true. And so we see a true showing up here telling us that just out of the first element, only considering our set as only containing 5, we can make a subset that adds up to 5 by picking the 5. But we can't do it for any other subsets. We can now see that our two subproblems that move in lockstep to the right are only going to encounter falses for the rest of the time. So false and false is always false. So or false is always false. Okay, on the next row, we now have an offset of 7. Okay, let's try and be a little more clever then. For 7, that means until we get to here, we only get falses out there. And what I said is falses don't affect us, so all that matters is the rest, which means we're really just copying down whatever we see above us until we get to 7. So we're just copying down. False and false is false, 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 false. Here we have a true and a false. Our offset now, 5 minus 7 is minus 2. That's still false out there, but the true here makes it a true. So we're just copying it down. And then here is when we finally get our second subproblem coming on the board, and it's a true, so we get a true. So again, two subproblems, 8 and 1. Those are both false. We can watch as they both move along. They keep being falses until we reach here where 12 minus our offset of 7 is 5, and we get a true, telling us we can make a subset that adds up to 12 by picking both of our values now. So we see here our second row rather has trues at 5, 7, and 12 because the sum of 5 and 7 are 12. So it makes sense. Okay, let's keep going and see if it keeps working. So 2, now our offset's only 2. So we only copy down a false here, and we're already at false or true. So we get true. False or false, false or false, true or false, copy down. False or false, true or true. Okay, that's obviously true, but let's stop here. What is true or true? This is the first time we've encountered true or true. We've had lots of false or false, that gives us all the falses, or we've had one true. But when we have true or true, that actually means there is 2 ways we can make this subset. One of them is not using this current value, 2, and one of them is using the current value, 2. Can we figure that out? Well, to make a subset that adds up to 7, we could either pick the 7 or the 5 and the 2. There's 2 combinations here. Okay, let's keep going. False and false, false and true. Add a 2 to a 7, we get a 9 now. That makes sense. Keep going, false and false, true and false, false and false. If we had a 14th column here, we'd get another true. We can now make a 14, but since we are only concerned with can we add up to 13, we stop here. Okay, let's keep going. Our offset's now 3, so we copy down 2. Now we get false or true. False or false is a false. True or true. There's 2 ways to add up to 5 now. False or false is false. True or false, 7. False or true. Now we can make an 8. True or false. We used to be able to make a 9. False or true. Adding on to the 7, we can add 3, get to 10 now. False or false, still no 11. True or true. There must be 2 ways to add up to 12 now. And false or false is false. Final offset is 9. That means all we're doing is copying the previous row until we get to location 9. So copy, 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 copy. Now it's true or true. Okay. True or false. Still true. False or true. We can make an 11 now, true or true, but false or false, still false. There's no way to make a subset that adds up to 13. Okay, so hopefully this convinces you if you believe our algorithm works properly. If not, you're going to have to go back to the brute force way of just trying all possible subsets. Now, how many possible subsets are there? Well, there are 5 elements here. 2 to the 5 is 32. You can go ahead and try all possible subsets if you like. Okay, if you do want an exercise, something else to practice on, here are a couple. Just try this again with a different subset. Make sure you understand the algorithm properly. Or try and modify this algorithm. A fun exercise that I think is to try and count the number of subsets, or modify it to find the one with minimum or maximum size. Okay, there might be a clever way to do that. All right. But keep in mind, all of these problems are probably just as hard as this, so don't expect to come up with anything more efficient than this. Just make variants of this code to see if you can use it to solve these problems. Okay, we talked a little bit about the runtime already, but I do want to finish this video talking about another problem, a closely related problem. So let's take a look at this here. Say we have a set of positive integers, so already very closely related, and you want to know if you can split the set into 2 sets with the same sum. So this is sort of about an equal division problem, and we can imagine equal division showing up in all kinds of problems. At the very least, maybe just equal division of some kind of reward among 2 parties. That seems to be something that probably occurs all the time. And I should mention a related problem to this is if any of you happen to be parents, or have parents, I hope, this is sort of a problem that parents sometimes face, which is if you have a child and you maybe want to give them a treat, and usually children get upset if they don't get the same size portion or the same amount, if it's not fair. And so the problem is, if maybe you want to give them a piece of cake, then they each get 1 piece of cake. It has to be the same size. Or if you give them a candy bar, then you want to make sure that you give them the same number of pieces of the candy bar and they're the same size. And so actually this problem sort of ties into our computer science problem here a little bit, in that candy bar designers, people who make candy bars, are very well aware of this problem. And what you will find is that candy bars, more often than not, are going to come in a prime number size of chunks, like a 5 or a 7 are sort of good examples. And the reason is a prime number will not be divisible by any number between them or beneath them. So, for instance, if you have a candy bar of size 7 and you have 2 children, there's no way to evenly divide it. Well, if you have 3 children, there's no way to evenly divide it, or 4, or 5, or 6. You must have 7 children if you want to evenly divide it, which that's a lot of work to just evenly divide candy bars. Of course, many clever parents came up with the idea, well, fine, I'll evenly divide it among the 2 of you and all the extra goes to me. I think that's a nice, fair way to go. But that design, the sort of marketing gimmick or scheme there that went behind that design is related to this problem, the idea of evenly dividing up some kind of resources. And I guess one thing that example shows to us is that in some cases it will be impossible to divide up the resources. Okay. Now this problem's a little bit trickier than just the candy bar case, because in this case our candy bar chunks are of different size. One's of size 5, one's of size 7, and so on. So here the question is there a way for us to divide this evenly into 2 sets? Okay. Now, we went through a process of formalizing this before for subset sum. This problem is actually very closely related. So what we're going to see here, there's 2 important changes. One, our target has disappeared. We're no longer asking what it adds up to. But Now we're asking it to add up to exactly the same amount as the set that isn't included. So these are the indexes in our set that we accept. These are the ones that we don't accept, the other ones that we've rejected. These ones should add up to the same amount to have an even split, an equal split. Okay. Our brute force algorithm is actually going to turn out to be the same here. But what I'm actually going to see or try and show here is that we could now go and develop a dynamic programming solution. It's going to look almost exactly to the one that we just did. Okay, we don't want to just copy it exactly, or rather, if we are going to copy it exactly, let's not just reproduce code. Let's just reuse what we've already got. So let's make a quick observation here. That if we add up all of our elements, let's say all of the s's in S, this is going to be the total sum of the set. Well, if we can evenly divide this into two sets, then this set should add up to 1/2 of this. Okay, each set should add up to 1/2 of this. So because of this, we can see, hey, this is like the target that we had in subset sum. If we can have a subset that adds up to this sum, then we can divide it evenly in half. And if we can divide it evenly in half, then it must have 1/2 that adds up to this sum. Both of those, so this is an if and only if relationship between these problems. And that's what we're going to actually use to cleverly solve our problem without having to reinvent the wheel. So here I have just a simple little piece of code. In this case, all I'm going to do is I'm going to take this sum. I've written it slightly different here, 1 to n of si. I'm going to let t be equal to 1/2 of this, and then I'm just going to call the subset sum code that we just wrote on the same set, no changes there, plus the target t. If it returns yes, we return yes, and if it returns no, we return no. Or if it returns a subset that adds up to t, that's the subset that is that adds up to half of the total. So this relationship that we've done here, we've actually shown a reduction from partition to subset sum. Now we've been doing reductions all up till here. We've been doing self-reductions. Now a self-reduction is from a problem to itself. Well, this is our first example of a problem to a different problem. And in fact, more often in computer science, we use reductions in this way, where we relate one problem to another one. It becomes a very useful tool for us to show that two problems have a specific relationship. And in fact, the relationship that I want us to sort of grasp here, that the reduction of partition to subset sum shows in at least some sense that partition is no harder than subset sum. Now what sense is that? Well, we just came up with one algorithm. We actually came up with two algorithms for subset sum. One was brute force and one was dynamic programming. And both of them were exponential. One was n2 to the n, one was n2 to the t. Both were exponential, and which one you should use depends on the relationship between n and t. Okay, so neither was necessarily better than the other. It depends on the relationship between n and t. Okay, now we could plug either one of those solutions in here to partition. And the runtime of partition, because this part's simple, the first bit takes almost no time at all. The runtime of partition is exactly the same as the runtime as subset sum in the big theta bound in the asymptotics. So what that means is we could say one of you out there comes up with a brilliant solution to subset sum, a polynomial time one. Say it takes, I don't know, n to the 4th, okay? Then we could go and take that and plug it right in here, and all of a sudden partition, its runtime becomes n to the 4th as well. And so this is what we mean when we say that partition is no harder than subset sum. As simple as we can make subset sum, any genius improvements we can make on subset sum in the future also become genius improvements on partition. So we don't need to solve this problem twice. And we're going to see in maybe a dozen videos from now a similar relationship with a lot of other problems as well. So this was intended mostly to be foreshadowing of those future videos. So if you're following along, watching the videos, stay tuned in future video for more details on this idea of a reduction. Okay. All right. There's a couple questions here. Can we show that subset sum reduces to partition? Can we reverse the roles? The answer is yes, but it's trickier, so I'll save that for another video down the road when we're focusing on reductions in more detail. And what this does is it allows to show that these two problems are equal in complexity, with a little asterisk on there at the end, but a very small asterisk. Equal in complexity meaning they need the same resources to solve. Okay, I think that's where I want to leave it for this video. This was intended primarily as another example of two-dimensional dynamic programming using subset sum as our main problem. But this last discussion on partition is just some foreshadowing about complexity theory, reductions, things we can look forward to in a few weeks and in a number of videos. So thanks for watching, and we'll see you in the next video.